First find out what is small ZL. Then we will require that we will reach a point from ZL, small ZL, to a point at AA dash where the input admittance is equal to 1 plus JB. Therefore, we will draw the G is equal to 1 circle or R is equal to 1 circle. So draw the R is equal to 1 circle, which we can use at G is equal to 1 circle using the Smith chart as an admittance chart. So we are going to use this Smith chart as an admittance chart. So draw this R is equal to 1 circle. On the right hand side you can see that this problem is translated actually into a circuit, a microstrip circuit. Microstrip line has characteristic impedance 75 ohms, and the stop is connected to the microstrip line of 75 ohm at a distance of L1 from the load end, and the length of the stop is L2. Characteristic impedance of the stop and characteristic impedance of the microstrip line are 75 ohm. In this stop, the stop end of the stop is short-circuited. The white dot that you see, that is written as short, that is the short-circuiting of the stop. Now, instead of one short-circuiting point, you can use many short-circuiting points, because when you connect top to the bottom using a wire or anything, any conductor from top to the bottom, when you connect that conductor has some inherent inductance. So to reduce the inductance, if you use many conductors in parallel, the inductances will be connected in parallel. So that will reduce parallel connection of inductance, will reduce the value of inductance. So that is why you require more number of stops. Instead of 1 point, if space permits, you use 2 or 3 points. Okay, now let us go to the actual solution. What we will do, locate ZL. ZL is equal to 1.2 minus J 1.6, and connect ZL to Z1 on the Smith chart. So connect that point. Then draw the VSWR circle with Z0 at the center and radius up to ZL. From Z0 to ZL, draw the VSWR circle. Then this circle, that then extend the line from ZL through Z0 to the outer circle of the chart. So when you do that, that will meet the constant VSWR circle at the point YL. So find out what is YL. Once you do that, you will find out what is YL. From YL, move along the constant VSWR circle to meet R is equal to 1 circle at Y1. So that Y1, read the value of Y1, that will be equal to 1 plus J 1.45. Then draw a line from the center, from Z0 to Y1 to the outer circle of the chart. From the outer circle, moving towards the generator, measure the separation in wavelength between Y2 and YL. What is the separation between Y2 and YL? Measure that. This separation is L1. So this separation will be equal to 0.1126 lambda. So that is the length L1. So easily we can find out what is the length L1, that we can find out in this one. So L1 is equal to 0.1126 lambda. This you can do easily. I am not spending more time, less time we will spend here. Then stop length we have to find out. From Y1, from the point Y1, move along R is equal to 1 circle to the Z0, find the reactive part of Y1, that is 1.45. For matching, this should cancel, so the length of the stop should be such that this 1.45 is cancelled at the point where stop is connected. So this should cancel. So the short-circuited stop should show an input susceptance of minus 1.45, because from the load we have found out is to be 1.45, that is to be cancelled by minus 1.45, minus J1.45. So that will do. So move from the short circuit point of the Smith chart. So locate the short circuit point on the Smith chart. Then move from the short circuit point that you can see the rightmost point on the Smith chart along the horizontal line. The rightmost point is the short circuit point when we are using it as an admittance chart. So the rightmost point is the short circuit point. So from there, move towards the generator. So move from the short circuit point on the circle or on the outer circle towards the generator to the point J1.45 and measure the length in terms of wavelengths as the stub length. So that is stub length is L2. L2 is equal to, now you can measure that length. That length will be 0.096 lambda. So once you do that, you have found out length of the stub, we have found out length of the section of the transmission line, length of the transmission line from the load up to which we should move or where the stub is to be connected. The distance from the load we have found out L1, length of the stub we have found out, so that solves the problem. So this is in short how you can do this. Then let us look at if you are given a problem, this is the problem. Then from the problem in terms of transmission line, solve it using the transmission line. So you can see here we have found out L1 to be 0.1126 lambda, L2 is equal to 0.096 lambda, characteristic impedance is 50 ohm for the stub and for the main line. So these are in terms of transmission line. Then transform the solution to microstrip line. So we have microstrip transform it to microstrip line in the form of microstrip line. Take a microstrip line from the load end of the microstrip line, move a distance of 0.1126 lambda. There you connect the stub or another microstrip line in this manner, the manner that is shown in the figure. And the outer end of the stub is to be short circuit. So short circuit, that stub length is L2, which is 0.096 lambda. So this gives you a solution. Then this is another solution you can do. Follow the same principle. Instead of using a short circuited stub, here we use a open circuited stub. So let us use open circuited stub here instead of a short circuited stub. So what we will do is first we will find out L1. So no problem in finding out L1. Follow the same principle of finding out L1. So I'm following the same principle of finding out L1. So go to ZL, connect ZL to Z0, extend that to the outside. So locate ZL is equal to 1.2 minus J1.6. Connect ZL to Z0 is equal to 1 on the chart. Extend that and draw the VSWR circle with Z0 as the center and radius up to ZL. Then it meets VSWR circle at YL. Extend this line that meets the VSWR circle at YL. Then from YL move along the VSWR circle to meet R is equal to 1 circle at Y1 is equal to 1 plus J 1.45. Draw a line from Z1 through Y1. So draw a line from Z1 through Y1 to the outer circle of the chart. From Z0 through Y1 to the outer circle of the chart. Then from the outer circle move towards the generator. Measure the separation in wavelength between Y2 and YL. On the outer circle, where it meets the outer circle, mark that as Y2. So then you measure what is the difference between Y2 and YL. The separation gives you L1. L1 is equal to 0.1126 lambda as in the previous case. So the length there is no change in length. Only change is in the stop length. So from Y1, move along R is equal to 1 circle to Z0. Find the reactive part of Y1, which is 1.45. For matching this, should cancel 1.45. Should cancel. So the stop length should be such that it occurs an impedance of minus J1.45. So we require a open circuited stop that should show an input susceptance of minus J1.45. Move from open circuit point on the circle, which is the leftmost point on the circle, towards the generator to the point minus J1.45 and measure the length in terms of wavelength. This stop length. So this will be L2, that is equal to 0.346 lambda. So we can use an open circuit, do this. The solution is same. Similar solution we can use here also. So this is about single stop matching. On the problem, there are problems with single stop matching. The problem let me discuss today before we stop. So let us discuss the problem. The problem is, in this case, you can see, we have to determine what is L1 or L, the distance between the stop and the load. Then the distance of the stop or length of the stop. These are the two things that we require to obtain. Now both these are dependent on the wavelength lambda g. Lambda g is dependent on frequency. So if there is a small change in frequency, these distances have to change. Which means if there is a change in frequency, either change in frequency or change in load, then we have to completely reconstruct it. So this kind of a single stop will not work. We have to remove the stop and locate it at another point. For example, suppose we have a coaxial cable. So at a distance of 3 cm from the end of the coaxial cable, at the end of the coaxial cable we have a load. Now from a distance of 3 cm from the load, we have connected the stop. After calculation everything, we have found out that the distance from the load is 3 cm. In terms of wavelength we have calculated it. Then from wavelength we have calculated it in terms of centimeter. So 3 cm or 5 cm from the load end, we have found out what is this. There we have drawn a hole on the coaxial cable. From the outer point we will draw a hole, take another coaxial cable, and then the center connected will pass through this hole and will be connected soldered to the center connector of the main line. Then the outer part will be soldered to the outer part of the main line. Now once the frequency changes, this matching will not work. So what we have to do is we have to change both this length and both the length of the stop and length from the load distance. These lengths have to be changed. So we have to throw this out. We have to design another thing. So that is very cumbersome and that is again costly. What we can do is, if we can fix this length from the load end to the stop, that we can fix somehow constant. Somehow that length we can stay fixed constant, and we will change only the stop length by using a plunger. So if you use a plunger, so just move the distance of the plunger, the stop length will change. So that will be a better solution. So for that we can if we can use two stops, that we'll see how we can do that using two stops. But that we can do using two stops. That is what is called double stop matching. Single stop matching, this is the problem, therefore we take double stop matching. In double stop matching, what we do is we take two stops, keep the distance between these two stops fixed, and we use these two stops on the main transmission line at a fixed distance from the load. Then we change the length of these two stops. If we change the length of these two stops appropriately, then they will be matched to the load. Now if the frequency changes, again we change the load, change this distance of these stops using plunger, or if the load changes, we can change the length of the stops using plunger. So that way it will be easier to match. That is what is double stop matching. We'll go to double stop matching. In the next class, we will discuss about double stop matching, complete the discussion of the double stop matching. Then that will take about half an hour. In half an hour, we will complete double stop matching. Then we will come back to your dipole antenna. We will discuss about how to design dipole antenna using HFSS. I will show you step by step. So if you are ready with HFSS, we will see how to design a dipole antenna using HFSS in a step-by-step manner in the next class. So that we will do in the next class. After that, in the last class, we will discuss about log periodic array, two types of array. One is called Aggie-Wood array and log periodic array. So to know that, we require this stop matching, etc. So that we have discussed now. Single stop matching, I hope you have understood. So we'll stop here for today. Please tell me if you have understood it or not.